Why would a power plant spend electricity at night just to pump water uphill? That sounds like wasting energy on purpose. But it's not waste. It's one of the smartest tricks on the modern grid, turning water and height into a giant rechargeable battery. Here's the simple idea. A pumped storage plant has two reservoirs, one higher, one lower. When the grid has extra electricity, like at night or during strong wind, motors run pumps that move water up to the upper reservoir. That's the charge. Later, when electricity demand spikes, the plant opens valves and lets the water flow back down through turbines. That's the discharge. You're not storing electricity directly. You're storing energy as elevated water, then converting it back to electricity exactly when you need it. The real battery here is gravity. If you lift mass upward, you store potential energy. Water is just a convenient mass because it's easy to move, easy to contain, and it flows through machinery cleanly. The higher the water sits, and the more water you store, the more energy you've banked. Think of it like stacking millions of tons of weight on a shelf. The shelf is the mountain. The charge level is literally the water level in the upper reservoir. So how does charging look in the real world? First, the plant connects to the grid like any other industrial load. When electricity is cheap or abundant, huge electric motors spin the pump. Many pump storage facilities use reversible pump turbines, basically one machine that can act like a pump in one direction and a turbine in the other. In pumping mode, it's not trying to produce power. It's consuming power to push water against gravity. And this is why pumped storage pairs so well with renewables. Wind and solar don't always match demand. Pumped storage is the grid's way of saying, fine, if power is flooding in right now, we'll store it for later. Now demand rises. Maybe it's morning and everyone turns on heaters, lights, and transit. Maybe it's a hot afternoon and air conditioners spike. The plant switches modes. Gates open. Water accelerates down large pipes called penstocks. That moving water hits turbine blades and spins a generator. Electromagnets and coils convert rotation into electricity, and transformers push it out to high-voltage lines. The key advantage is control. Unlike a normal river dam that depends on natural inflow, pumped storage can generate whenever the grid needs it, because the fuel is water you already lifted. Let's be honest, you don't get 100% back. You lose energy in several places: friction in the pipes, turbulence in the flow, pump losses, generator heat, and electrical conversion. But the round-trip efficiency is still high enough to be worth it. The point isn't making free energy. The point is time-shifting energy. You're buying electricity when it's cheap and plentiful, storing it, then delivering it when it's scarce and valuable. That's why pumped storage exists. It's a grid stabilizer, not a magic generator. Power grids are unforgiving. Supply and demand must match continuously. If they don't, frequency drifts, equipment trips, and outages cascade. Pumped storage helps because it can respond quickly. It can ramp output fast to cover sudden losses, like when a large generator unexpectedly shuts down. It can also absorb excess energy by pumping, preventing overgeneration when wind is strong or solar is peaking. In other words, it behaves like a shock absorber for the entire electrical system, smoothing surges, filling dips, and keeping everything steady. So how big is this battery? The stored energy depends on three things: how much water you move, how high you lift it, and gravity. If you double the water volume, you roughly double the stored energy. If you increase the height difference between reservoirs, you store more energy per unit of water. That's why pumped storage favors mountainous terrain or deep valleys. It's literally using geography as a storage medium. And unlike chemical batteries, the storage material, water, doesn't wear out. The reservoirs don't degrade because you charge them too many times. The main wear is mechanical, and engineers design around that with maintenance and robust components. If it's so good, why isn't every city running on pumped storage? Because location matters. You need land, a meaningful height difference, stable geology for tunnels, and reservoirs that can be built safely. You also have to manage environmental impact. Some designs use closed-loop systems, reservoirs that are not connected to rivers, to reduce ecosystem disruption. But there's still construction, permitting, and cost. It's heavy civil engineering on a massive scale. Pumped storage is powerful, but it's picky. As the grid adds more wind and solar, long-duration storage becomes more valuable. That's why pumped storage keeps coming back in energy plans. People even explore new versions, using old mines, quarries, or other engineered basins where the geography is already there. Same principle every time. Electricity becomes height. Height becomes electricity when you decide. So here's the question. If you had to choose one for your city, pumped storage or giant lithium battery farms, what would you pick and why?